So let's continue. The thing with tracking is that it actually has to compare images or features in the image in order to make it possible. And working with the whole image, in particular if you have 3D data or 4D data, is very time consuming and also may overload your computer. So what instead, an alternative way is to work with key points. So you identify characteristic points in the images. And the important thing here is that these key points, there must be some kind of corners of most interest. And they should also be uniquely identified between images in order to make them useful. Also, if something is moving, rotating or something. One way of doing it is using the Harris corner detector. And here we apply, so it's in principle a sequence of filters that identifies corner properties in the image. And if we have the raw image, just this skewed checkerboard, and compute the corner features, you can see that you get nice high intensity points on each corner. And these are then identified here and plotted together. And this can then be used in order to identify our data or relevant points in our data. So using this bone slice example and running the Harris peaks, you may see that there are some white dots here, but overlaying them on the image, you can see that it actually identifies pretty good, very many features within the image. And that is what we need. And when we have this, then we can do this one-to-one comparison, for example, for the least square or approach, or shortest nearest neighbor approach, sorry. Then we have reduced the amount of data that we need to do for the nearest neighbor, and then we can speed up the whole process. The important thing with these corner points, then have to be very stable and also fixed on the features, so we can't have that a corner point is moving between the images. That wouldn't be very helpful. So we need to have something that really is unique for each corner. And also it should be independent of translation, rotation and shear. So let's see how well the Harris detector can cope with that in this little movie here. And then you can see, you can move out. So you can see how the corners, they stay really very well on the markers stay very well on the corners, and they follow all the way. So that looks like this could be a pretty good choice for the purpose. Another thing that we can add is some kind of descriptor. So that's a binary code that describes the neighborhood around these corners. And there are different types of such codes. There is an orb algorithm, and then there's one called fast and one called brief. And there are some references to these as well. So these are underlined, so if you click on the links in your document, you can read more about these. But in principle, what it does is looks in the neighborhood and looks if the value in that neighborhood is above or below some threshold, and that gives you this bit chain. And this bit chain is then unique for each neighborhood. And so let's create some data. We have the bone image again. We apply some blurring and also some transformation. In this case, we just do delta x plus 15 and delta y minus 15. and that is the movement we apply to this image. So it's a small shift. And then we try working with the brief descriptor, and yeah, it finds some relevant points, but you can see also that it's not really good at identifying them. It has some very, it actually only has 2 hits, one down here and one very long distance. And the short one, of course, looks like it matches pretty well between the images, but the one with the long distance here actually didn't grab the right item. So it got a bit confused because this feature here almost looks the same like this one, and then that's why it got confused. If we try the orb descriptor instead, it's much better, it seems, for this kind of image. In principle, you have to test which kind of descriptor you use if it matches what your special use case requires. Now this one makes a very good match among most of them, and then there's one that got confused. But that one can be rejected. So if you get, so you can in principle reject it that it is far, far longer than all the others. So that's kind of an indication that this one can be rejected. And then we can also, once we have done the tracking, we can also, on these vector fields, we can start doing some averaging to get a higher level information. And here you can do different types of averaging. You can do it spatially, so you do it only in the frame. You can do it temporally, so you do an averaging along the time, or you can do both. So let's return to this -1, data set and see what we can do. Well, this is the bookkeeping code that actually goes through all the frames and prepares a data frame for us. I'm not going into details, but anyway, here we have the spatial averaging illustrated. So you have averaging within each frame, and then you're not looking at what's happening between time points. And then we can get some kind of flow like this, where we have, in principle, we can get an average effect over the whole image that gives us these arrow effects. So this is just the position, and here we have the dx and dy's. Then when we do temporarily averaging, then we go then we don't look at the neighborhood in space, but we only look between the frames. And that is actually also something that is done pretty much, that you have kind of a running average effect between the images, not only when you have the vector fields, but also if you want to smooth over time, you can have a running average or moving average. Different people say different things. Sometimes I use one or the other, but I think the mathematical correct is moving average. That is what this statistical literature says. And then we can do that, and we can see that in every time step we have a trend that it goes actually -1 between the steps. Yeah. And then we have the whole thing where we do both, and we can get an averaging effect that gives us a little bit of time flow between the steps. And you can see here how the field is moving upwards in the different time steps. Then we create here a longer time series with some more coordinates. It's a little bit more complicated. So it's moving not only straight up, but actually also going kind of a staircase movement like this. And here we can do some tracking. We can see down here that the tracking gives us, in general, perceived movement is still going up in the upper left corner, even though it's going a little bit staircased. And what is happening here is that the X component is sometimes not moving, and then it's doing -1, not moving, -1, and so on. And the Y is then offset a little bit. And if we look at the other averaging here, we have that it's always going one like that, one left, one down, one left, one down. So that is the kind of trend averaging you can get out of that. And if we look at this longer series, you can also see here how it flips around over the time steps. Yeah, so these are a little bit on averaging. Tracking is a tricky task, and fortunately, many people have been occupied with it so much that they have made a TrackPy module for Python, and there are plenty of applications. And if you want to work with tracking, I think this is probably a good starting point for your work, instead of writing your own tracking nearest neighbor, which probably would fail because it's too simple. But anyway, there is also a tutorial on their webpage showing how you can try. I think it's actually all these examples here are from different tutorials that you can do. So tracking is, first of all, you have to find the right algorithm for it, but it also has sensitivities of different types. So one thing is random appearance or disappearance, or actually just going out of the edge and then coming back again. These are tricky things that needs to be handled somehow in the tracking. If all items are in the frame all the time, then you're good, but usually in a practical experiment, there is always one that goes astray somehow, going out and coming in or something like that. Then it's also how you segment your images in the data, how well you identify the items. If the watershed is doing its thing, if you have two items that perfectly overlap, then it would be the same, and the tracking would be also confused. And of course, the crossed path that I showed with the sine curves before is also a problem, that then it may go in the wrong direction. So there are quite many things to keep an eye up on when you start doing the tracking. So the jitter, we have in principle, we have a deterministic trajectory of the data. And then on top of it, there is some uncertainty in how it moves. And this slide I produced just before not Christmas, but Easter last year. So that's why I have a bunny. But anyway, if the bunny is jumping, you would kind of expect deterministically it would land about here. But then thanks to the jitter, you have a jitter amplitude and the jitter orientation, you maybe land somewhere within this yellow area. And that is the area uncertainty, and that is also the uncertainty in the whole tracking approach that you are using. So this is something that needs to be taken care of in your tracking algorithm. And of course, we also have the other limitations. We have the flow rate, we have flow type, we have density of items, and so on. Also particle uniqueness. It's much easier to have items that have very distinct, unique shapes than if you just have, like in the snowfall, only round objects. Maybe they're changing shape, size a bit, but the more uniqueness you have in the particles, the easier it is to track, because then you can add that also into the a priori for the selection. So, how you can improve it? Of course, you can increase the acquisition rate, or you can either by changing the camera or by slow down your process, if possible. You can also change the resolution, and that, again, changing camera resolution, or also the density of items you have in the field of view. And of course, you may need to change the field of view as well. So there's quite many things that you can change in the acquisition, but also in the experimental parameters, how you control what items you have to track. And sometimes you can even do some kind of flow simulation, seeing how different tracks move. So in this case, it would be a motion which should go vertically, and then it has some jitter of the direction, and that gives a little bit this wormy behavior of the tracks. So that could be a way to see how well your method is working. Difficult is probably when you have a random walk, because that goes pretty wild. Then you can't use any a priori knowledge, or you can use the statistic model of the random walk. Yeah, so this is a way, the simulations is a way how you can, that can help you to find the right parameters for your work. And then you can also test the sensitivity to how much the jitter actually does. And then there's a question, how much is precise enough? It could be that if you just have a 5% error in the bubble position, you may think you are good. That would potentially, so this is just a made up example, but it may potentially give 5% in the flow field, less than 5% in the flow field, which would be good. But it may give a more than 20% error in topology, and that may not be good. If you do look at the errors in shape or volume, it would maybe be, in some cases, 5% of the distribution changes may be okay, but then there would be maybe more than 5% of individual bubbles that change behavior, and maybe some strain tensor calculation also goes completely berserk. So you have to see the effect of the precision in what you do and what you want to see in the end, and how that actually affects. So it's the whole cascade of what you're measuring, and see how these errors propagate. Then you can also add a lot of different extra requirements on the tracking, the metrics that you use. Here are some different proposals. So bijective requirement, maximum displacement. Then you can continue doing a lot of different, so you can, here is one, for example, with prior and expected moment. In this case, you actually, with the help of derivative, project, I expect my next dot to be over there, and looking with the help of the, maybe even the uncertainty region, and then you can improve your quality. And that would probably also help us with the sine curves to get beyond the crossings, because then it would point in ways that makes it clear. There are quite many of these different criteria. Then you can even go towards physics-based models, that it's not physical that it goes backwards, for example, or it's not physical to change shape this much. Who knows? If you want to go really into complex algorithms, you can also look for Kalman filters, which are an optimal filter for the tracking. That has been used quite a lot for tracking tasks. So also going back even to the radar technology, where they look at trajectories of airplanes on the radar map. So there are quite many approaches here to get the best metric. Then we can go on with more advanced approaches. We can also look for hypothesis testing that includes more information between the data sets, or the steps. and that can also help us to see if there are multiple paths to explore, and see if even in some cases you come to the point that you have splitting or merging, and that requires also some extra thinking, so maybe there you need also some more advanced approaches. So that was looking at identified items. Now we look at the images again, and voxel-based approaches. And what we can do to find shifts between images is to use correlation. So we compute the correlation between images, and this can be done using a correlation operation like this, or we can also do it in the Fourier space. Depending on the size of the image, the Fourier space may be actually faster to do. So it's in principle just the Fourier transform of the image itself times the complex conjugate of the second image, and then do the inverse transform. So correlation in 1D is quite nice. I produce a little example here where I have two peaks with some noise, and to measure the position between them with the help of correlation. In this case, it would probably even be possible to compute the difference between the positions of the two maximum peaks. But let's bring in the big hammer and do the correlation. And what it gives, we compute the Fourier transform of these two, and do the multiplication and back in real space again. And what we get is actually we can see that the shift here is what I added to the images. So it's actually a shift of 6, because these peaks, they were at 10 and 4. So we can see that there is actually a shift, and we get a very beautiful peak where they have moved. Let's try some of these metrics also on a little image. So let's load the MNIST5 number here and do a little bit of shifting. In this case, it was -3 + 2. So we go up in the upper right corner, and we want to see how much this feature was moving. And again, we do some kind of correlation here, and computing the sums. And there are some practical issues with this, because when we compute the correlation and move around the items, then we have to move somehow. So it's a translation, rotate, or rolling of the image, or something like this. And if we have just a narrow field like we have in this case, so you can see that this image just more or less covers the 5 itself, and there's not much space. So if we roll it, so just moving a pixel row and fill in the other one at the bottom, then it can easily happen that we get images like this, and they are not really looking like what we had in the beginning. So what we need to do is to pad the image around it, at least with the distance that we want to do our scan with the correlation, and then we can handle it pretty well, and without these distortions. So looking at how this one is moving around, we do a little bit of a scan. So we are moving the 5 and computing this correlation sum between them. And at some point we see that, wow, there is our point. This 5 is a little bit special because it produces 2 maxima with the same value. So there must be something strange with it. But anyway, it gives us essentially the position of the shift, a peak at the shift in the image. And then of course we can look at other metrics. We can look at mean squared error or root mean squared error and look for the minima instead. And that would also produce images that give the same shift. And then, as we did before, we can also do the Fourier transform The Fourier transform of the images are not so easy to interpret. You can't see any difference between them, but when you multiply them and go back in real space, we have a nice positioning of the displacement. And this one I didn't update the image for this one. Anyway, so a thing that we want to do often when we have time series is that there may be some motion of the objects. They are not still. So for example, if you have a patient looking at something between different times, they are definitely not aligned. It's not possible. So what we need to do is to get them exactly in the same grid. So let's say we have two images and we want to get them right. So first we need to flip it and then we move it until they perfectly match on each other. This is the wrong image because I'm not using it in the next slides. But anyway, what we do in this case, we just look at the little small region that we want to register. And then there is some code here, mainly for doing the animation and showing how it's moving around. And this gives us at least, for our first example, we have this displacement of minus 15 and 15, and it gives us, with the correlation, gives us some displacement position, which actually matches the real thing. We can also try the same thing with the sand grains and do the same thing. And this time I did the correlation in Fourier space, and we beautifully see the peak at the minus 20 and plus 30. A half is more like a numeric effect that I didn't sort out. But in principle, we can fetch that displacement pretty well. And now I come to the registration. So the process that we have two images, and in principle we have one moving image that has been taken later, and then we have a fixed image that we don't move, and that's often also called the reference image. And we are now going to use the ITK, or the Python implementation of ITK. The original ITK was implemented in C++, but they have now done a Python port to it. And typically what we need to do is we have our fixed image, and we have our moving image, and we define some kind of transform, how to bring it into the same frame as the fixed image. So we take the moving image, we let it transform using some kind of interpolator, and then we compare with a metric to see how well was the match. And that is only one step. So what we really need is actually an optimizer that takes the whole and bring it up into this kind of automatic registration algorithm. So we have the moving image, we have an interpolator, and the transform. It's compared with a fixed image, and then it's sent into the optimizer, which is often some kind of gradient descent or algorithm that tracks up how to move the object. And what is happening is that the optimizer is then telling the transform, update yourself. This is the new transform that we have to apply, and then it applies again, and it iterates until you reach some kind of stability. So we have these fixed images and moving images, and the transformations that we can do are the affine transformations. We have the translations, we have scaling, we have shearing, and in some cases we even do deformable transforms. So that is that different places in the image are moved around a little bit differently. And that may be needed, for example, also in use cases with patients. Organs change shape depending on the state of the patient or even time of the day. And also, if we have, say, mechanical load conditions of a structure, it also may deform. So these are things that we, transforms that we need to apply. Then the interpolator, we can do different types depending on also the effort we want to spend. Sorry. The nearest neighbor is very easy to implement, also fast. And then with increase in complexity, we go through bilinear, bicubic, B-spline, other kinds, maybe. And then you get more precise in this interpolation. Initially, in the first iterations, before you know where you are, maybe you want to run the nearest neighbor. And then when you come closer to the real spot, then you go for more advanced types of interpolators. The metric, there are pretty many metrics to work with here. The basic one would be the mean squared error. Then we could do a structure similarity metric. Could you also use a correlation factor? And there are also other metrics depending on the type of data that you are working with. And then, of course, last step, we have the optimizer, which also drives the transformation part to the right position. These are typical ones that you see in machine learning, but there are other ones also implemented in the ITK. And well, this one is just some code for the visualization that I'm doing. I actually planned to hide this, but I didn't. But here we have our image that we are playing with. So it's just some kind of porous material with some grains in it that are packed together. What I did, I just cut out two pieces, the red one and the green one. And these are the images. You can see that there's 20 and minus 10 displacement of this. I didn't introduce any rotation in this example, so we only have linear transformations. And now our workflow is, first of all, to define a registration model, and then we add a transformer to it, we add a metric, and then we add an optimizer. And all this, I spare you for the code, so if you want to look at this process, everything is in this registration.py file, which I still need to upload on the repository. So let's try. Mean squared error metric is the basic one. It's very easy and often a first go-to when you want to compare images. And what's happening, it's we see here, we run the registration and show the results. And what you can see first is that the distance to target in the beginning is quite far. And then after about 40 iterations, we come down to some kind of convergence. And then it does some funny bumps here, and then at some point it stops. And what we see of the trajectory, so this is a plot of the positions, is that it first makes some jump, it goes in the wrong direction, realizes it, and comes back on track and goes pretty straight up to the endpoint. And then you see some funny jumps around here. These jumps are an artifact of the optimizer, which doesn't trust that it found the perfect minimum in the trajectory search. So it sends off a random test to somewhere a little bit away from the found point, just to see if it finds another track to go onto. And this is also what you see here in the distance to target, that it kind of tries a little bit to convince itself that it actually found the perfect minimum. And then we look at the registered image, and original minus registered. There is some kind of shift, which I haven't really understand why it should be there. Maybe I did some kind of stupid transformation when I presented it here. Interesting thing is also you have this black band, and that is because there is no information here. So if you have two images that are not perfectly overlapping, there is actually not perfect overlapping information in both. So that is what you see here as this black band. We can try a different one. You saw now that this one did registration in 40 iterations. If we try the correlation metric, we can actually find something again, but this time we do it within 20 iterations. So the correlation apparently was better on this one. So you have to try a little bit which metric is the best for your type of data. And you want to start with the easy ones because they are faster to process, and if you have much data, you want to save every second you can. And here's another one called the histogram mutual information metric. This is a funny one. When you look at the trajectory, it kind of walks around a bit, and then all of a sudden it finds the way how to go there. It actually also finds a pretty decent position in the end. It took actually up to 50 iterations for it to get there, so it was a bit confused in the beginning, probably because this has so many structures that are about the same. Another thing is this image that we looked at, it has essentially only two levels, so it's flat regions. And that's like being slipping around on ice. It's not easy to grab it. And it would be much easier if you had intensity distributions that are more like cups, and then they would easily hop up and grab each other. And that is what I try to show here. So you have these flat regions, it's like this. They're sliding a little bit and trying to find the right thing. But if you have these peaks, they're really the cups that grab on each other. So if we try with a different gradient, so let's modify our original image, do some thresholding. This was just an arbitrary. You don't have to do any very precise thresholding here. And then compute the distance map, then you get all these bumps. So it's in principle the cups that I mentioned. And if we try again now, running the mean squared error, you can see that the mean squared error pretty quick finds the solution. It goes straight to the point, does a little bit juggling here, and then it's done. But the interesting thing is, before, on the flat surfaces, it needed 40 iterations. Now I could do it in 10. So by modifying the images, you can also make it easier for the registration to find the right spot. And yeah, then we can compare some losses and how it works. Another thing is also initial guess. These registration techniques, the more complicated or the image is, or actually if you have too many very similar structures or patterns, it's very hard for the registration to find the right spot. So you have to kind of give it the first position to know where it should start, or actually prepare the images in a way that you only have to move some few pixels to guess the perfect alignment. A tricky case is, for example, if you have a cylinder which is high contrast to the background, but inside you have the small relevant items. It easily finds, oh, there is a cylinder, but then the last rotation to find the structures inside can be very hard. So it often helps the algorithm if you can rotate it, pre-rotate it a bit in the right way to give it an initial guess that works well. And oh, I'm running away in time today. The other thing we also have is looking at local changes between images. And until now, we looked at the correlation for the global case. But instead, if we want to look at local displacements, let's say this one, and then you compute the correlation on all points in the neighborhood, with that, you can see the non-rigid changes, and that is where we come to the digital volume correlation. And that is something that is used to introduce the physics and understand the strain effects in the images. And they are really able nowadays with the algorithms to come to the point that they are looking at sub-pixel displacements in the images, and with also confirmed it experimentally that it's actually is sub-pixel displacements are real. So that could be to tell what kind of deformation we have on the objects when we apply some load on the data. So we can quantify this strain, so we have some kind of delta L over L, which tells how the object has changed in shape locally. And then we can also compute the strain tensor. And one example of this is, we have different types of strain. We have volumetric and deviatoric, and it depends a little bit on what you are looking for, to what you focus on here. And here is an example that was done looking at shear bands in drill cores of a rock, where they wanted to look at the water distribution and its displacement, or the water distribution depending on where you have a shear band. So this core, they introduced 2 notches and applied a force, and then you could very beautifully, with this digital volume correlation, you could see really where the plane was, where it started to skew, and in this shear band. And well, that brings me to the end of this part. I was talking a lot today, so I plan to do also a part about visualization, but I shift that to next week. And next week I will not be standing here, so it will be a pre-recorded lecture, which I will upload during next week. Sorry for not being here, but yeah, I needed to go to a conference, so that was. But this is the only time I'm away from the lecture. But you will get the recording. Okay, thank you for today.